value, which is the strength by itself, and then the viscoelastic property or the phase angle. And phase angle is really related to both viscous part and the elastic part. That's what you see here. So phase angle is a ratio of the viscous part to the elastic. And both of them are there, inherent characteristics of the material. So we came up with a different figure that you saw before, a sinusoidal figure. And phase angle is one of the outcomes of the experiment. So if the value of phase angle was between 0 and 5, basically the material is elastic. Okay, something like concrete. Okay, so it really emanates a lot of noise. That's the hypothesis. We still need to validate. How did we validate it? We'll see that later. So if it was between 5 and 45 degrees, which is normal value, okay, that's what we have seen historically over the last 50 years. And that's viscoelastic part, slightly less noise. And if it was higher than 45, it was quieter. And we will see how were we right with this hypothesis or not. Okay, so this is a relationship. This is average relationship of whatever mixtures we had. Okay, 100, 200 mixtures or so. This is a relationship between the dynamic modulus, which is one outcome of the experiment, and the other outcome is the phase angle, which is a viscoelastic property. So, as I told you, if you remember, we ran it at 5 different temperatures and 6 frequencies. So at the lowest temperature, when the material is really stiff, really like concrete, okay, there's no movement of particles, the phase angle value is really low, between 0 and 5. Although you don't find 0 values, about 2 to 3. Okay. With increasing temperature, you see that the values of phase angle also increase. Now I'm talking about the conventional mixtures. And then it reaches a peak, fairly about 30 or 35 Celsius, which is about 100 to 120 Fahrenheit. And then it starts to diminish. Why does that happen? Mainly because the binder or the asphalt starts to play a less role, and the aggregate skeleton takes part, and then that dominates the effect. Okay, so basically asphalt mixtures have 3 different components, if you recall. One of them is the asphalt binder by itself, then there is rock, then there is air voids, which is still a component. Then if you have rubber in the mix, it's the other component. Otherwise there is no rubber, then it becomes a conventional mix, right? So at higher temperatures, binder stops playing the role, and the aggregate skeleton takes part. So the phase angle starts to diminish. So do you expect it to go all the way to 0? Yes, of course. If you run the experiment at, let's say, 70 Celsius, which is about 140, 150 Fahrenheit, when you cannot really run the experiment, but theoretically, yes, the phase angle becomes 0. It becomes really elastic because you are just testing a rock. Okay? When we saw the data coming from the asphalt rubber open grade or the friction coarse materials, which had higher binder content in it by itself and higher air voids, we didn't see that effect at the highest temperature that we tested. But presumably, theoretically also, it can go down. Okay, but we really did not know at what temperature. So basically, we didn't have a peak for an asphalt rubber mix. So phase angle is still a distinguishing parameter. Okay, so that's one thing that we got out of this analysis. So here is the statistics of the mixtures. Although we had about 300 mixtures, all of them were not run at 5 temperatures. Okay, so those that were run using the current protocol were only about 200 mixtures, about 180. This is coming from 2008. So after that, we have more data that has been added to the database. So 163 conventional mixtures. The peak was 39. Remember that peak that you have seen after a certain temperature. The peak was 51, meaning the highest value of phase angle, after which it didn't fall. 45 for a gap graded mix. There are 2 different mixtures in asphalt rubber by itself, 2 different gradations. Then we also tested a Portland cement concrete, which is still against the protocol. Okay, but we saw that the value of Phase angle was about 5. We just said 5, okay, it was really not 5, or 2 or 3. That was the lowest that we could see. But we just tested one sample. Okay, now, we also did some statistical analysis, simple statistics, between asphalt rubber mixtures and conventional. Are these values really significant? And we did see that there is significance between asphalt rubber mixtures and conventional in terms of just the average values and standard deviation. Okay, this is the basic simple statistics that we did. Before we move on, you can see here that the asphalt content or the binder content in the mix changed from conventional to an asphalt rubber mix. As I told you, there is higher binder or higher asphalt content in asphalt rubber mixtures, mainly to account for the rubber that you input. If you input a different modifier, you'll have to account for more binder. Okay, so that's why you have higher binder in asphalt rubber mixtures when you compare with a conventional dense gradient. Also, the air void values were really high for asphalt rubber mixtures, mainly making them porous mixtures. So between 18 and 22% on an average, versus about 4 to 5% or 7% for conventional mixtures. The other thing was, since we run it at 5 temperatures, we wanted to see how it changes with temperature. And as you see here, 3 different mixtures, asphalt rubber versus conventional. You see that even at higher temperatures, the values for phase angle for asphalt rubber mixtures are higher when you compare it with conventional. Okay, so we found a model that related noise and temperature. It was developed in France. So it also accounts for the road surface temperature coefficient. As I told you, there is the temperature effect on asphalt mixtures, okay, because it's a viscoelastic material. And with using this model and the experiments that we ran at different temperatures, we found that with increase in temperature, since the material becomes more viscous, and the binder effect starts to be more pronounced at those temperatures, the noise value starts to decrease. And we have seen this in field as well. In Phoenix, we have seen that the values are really low at 2 different temperatures. Okay, during summer, the values of noise are really low when you compare it with winter. Okay, that's what you see here, using the model. So there was a significant difference in phase angle with change in temperature as well. This slide is slightly complicated, more of theory, more science. 3 different components of the E-star test, one of them being the stiffness, and you see the green line here. So basically it's E-star versus E-star, or the stiffness versus stiffness, and then the different components. Okay, E-star versus E prime, which is the elastic component of the mix, and also the phase angle. As you have seen before already, the phase angle starts to increase with increase in temperature, and then it reaches a peak and then starts to drop at higher temperatures. Okay. How did we observe this with real data? So if this is theory, here it is. So this is a conventional mix versus an asphalt rubber. The value of phase angle that you see here, okay, that's in green here. It starts to increase and reaches a peak and then drops, that you have seen before. Asphalt rubber mix, it increases and there is no drop. So if you actually go to the definition of phase angle, it has some relationship with viscous component and elastic, if you have seen in the first few slides. So if you translate this to those 2 components, what happens? There is a difference between E prime and E double prime, meaning loss and viscous. Tan 45, tangent of 45 degrees is 1, right? And phase angle is actually ratio of loss modulus to storage, which is E double prime over E prime. So if it is 1, E prime should become E double prime, or loss modulus should equate to viscous, elastic. Elastic should become equal to loss. But here you don't see that because the difference is 30 degrees. But in the case of asphalt rubber, it was greater than 45. So we really achieved a phase angle of 45, wherein tan 45 becomes 1, where E prime and E double prime, meaning loss and storage, they both equate, which is what you expect material to have a higher viscous effect and probably lower noise, meaning the material becomes softer with higher phase angle. Okay, so what could we do with that data? We researched if there was any master curve that could be developed using the data that we had for 5 different temperatures on 6 frequencies. You can have raw data, okay, but if you don't have one single plot that can distinguish or that can be used to actually procure the phase angle at different frequencies and temperature, it's useless. So there was no phase angle master curve. So basically the concept of time temperature superposition principle applies here. So this is a 3-dimensional figure. So you have frequency and temperature in one single curve. The stiffness master curve is already there, or the Easter master curve has already been generated over the years. The phase angle master curve was not generated, so we thought, okay, maybe we should do something with the data that we had. So you are normalizing everything to one single temperature, which is basically the intermediate mid temperature, which is 21 Celsius or 70 Fahrenheit. Because we ran it at 5 different temperatures, we had one mid temperature. So we could normalize everything to one temperature. More of a complicated thing, but you're basically reducing the time or frequency. So it's basically time frequency domain plot. It's a 2-dimensional or 3-dimensional problem where you can have phase angle at different frequencies and temperature on one single curve. So we had, this is the predicted versus the measured phase angle values using the master curve for about 6,500 points. It's really an excellent correlation that you see. And then we also developed phase angle predictive equation. Let's say you don't have the instrument to test, okay? But you had the mix design, meaning you had the asphalt content for the mix, you had the gradations. So can you actually predict phase angle? Yes, we could using this equation. I know a lot of coefficients here, but if you know 2 values, you can calculate the rest. That's the volumetric mix design. Some of you know it here, right? You should be knowing it from materials class. PFA, VMA, all of them are related to asphalt content. So if you know 2 values, you can calculate the rest. And the R square value was really high, coefficient of determination. And we developed separate equations for different mixtures. We had to do it, mainly because you didn't see that peak for an asphalt rubber mix.
Krishna, I have a question. I don't know a lot about this pavement stuff, so this might be a stupid question. But so this is an empirically driven equation, right?
No, this is coming from the data.
So yeah, that's what I mean by empirically driven.
Yeah, empirically, yes.
So it's all these coefficients like A dot, A1, whatever. So you calibrate that using the data that you obtain.
Mm-hmm.
So do you do some kind of testing? I mean, you know, which model is better? I mean, all these variables, are they significant?
Yes, after making sure that these variables are significant, we came up with this model. But again, this can be enhanced. We haven't done it so far. Okay, this is the only model out there in the world right now. And this was not even there before. So we thought we should do this as well. As I told you, you just need the mix design. We actually had more than double coefficients. Okay, we came up with only, I think there were 22 here. Isn't that, yes, 22. We had more than 50 variables here. We came up with 22. But I anticipate that we can go further and making it better. So we can make it better. Right now, this is a non-linear, meaning it's still, you see, it's still a linear model. Okay, but we can make it in terms. We can change this. One of the ideas will be to change this.